Have you ever wondered why Redis is consistently the go-to choice when millisecond latency is non-negotiable? Most traditional databases like MySQL or PostgreSQL are designed to handle massive amounts of data by storing it on a physical disk. While modern SSDs are fast, they still require a physical I/O operation to fetch data. Redis, however, flips the script by living entirely in the system's RAM. Accessing data from memory is orders of magnitude faster than fetching it from a disk. We're talking nanoseconds versus milliseconds. In this video, we are going to peel back the layers of the Redis onion to see the clever engineering tricks that make it a speed demon. It isn't just about being in memory, it's about how that memory is managed and accessed. Let's dive into the hidden architecture of Redis.
One of the most counterintuitive facts about Redis is that it is primarily single-threaded. You might think that more threads equals more speed, especially in our multi-core world. However, multi-threading brings a massive overhead called context switching. When multiple threads compete for the same data, the CPU spends significant time managing locks and synchronizing state. Redis avoids this entirely. By running commands on a single thread, it eliminates the need for complex locking mechanisms. It processes requests one by one, but because it's in memory, each request is lightning fast. It's like a world-class chef working alone in a perfectly organized kitchen. No one gets in the way, no one bumps into each other, and orders fly out the door at record speed. This simplicity is the secret to its high throughput.
If Redis is single-threaded, how does it handle thousands of concurrent connections without blocking? The answer is I/O multiplexing. Redis uses a mechanism called an event loop, typically powered by system calls like epl on Linux. Instead of the CPU waiting for a network socket to send data, the operating system notifies Redis only when there is something to do. This means Redis can manage thousands of open connections simultaneously while only using a single thread for execution. It's like a master waiter and doesn't stand at one table waiting for a customer to choose their drink. Instead, they move around the room, only stopping when a customer raises their hand. This asynchronous nature allows Redis to handle massive traffic with very low resource consumption.
Redis isn't just a simple key-value store, it's a data structure store. This is a crucial distinction. In many databases, to update a list, you'd have to fetch the whole list, modify it in your application, and send it back. Redis allows you to perform these operations directly on the server. It implements highly optimized versions of strings, lists, sets, and hashes. For instance, it uses zip lists for small lists to save memory, and skip lists for sorted sets to ensure fast searching. These structures are written in C, optimized for memory layout and CPU cache hits. By doing the heavy lifting on the server side with optimized C code, Redis reduces the amount of data transferred over the network and speeds up complex operations.
Often, the slowest part of a database operation isn't the execution itself, but the network round-trip time. Every time your app sends a command, it waits for a response. If you have 100 commands, that's 100 trips back and forth. Redis supports pipelining, which allows a client to send multiple commands at once without waiting for the individual replies. The server processes all the commands and sends back a single consolidated response. This significantly boosts performance for bulk operations by saturating the network bandwidth effectively. It's like sending one large delivery truck instead of 100 tiny scooters. Pipelining combined with Redis's speed makes it possible to process millions of operations per second on a single instance.
A common question is, what happens if the power goes out? Do I lose everything? Even though Redis is an in-memory database, it provides persistence options. The two main types are RDB, which takes snapshots of your data at intervals, and AOF, which logs every write operation. Now, you might think logging to disk would slow Redis down. However, Redis performs these persistence tasks in the background using a mechanism called forking. A child process is created to handle the disk I/O, while the main thread continues to serve client requests at full speed. This ensures that you get the durability of a disk-based database with the performance of an in-memory one. It's the best of both worlds, and it's handled with surgical precision.
To wrap things up, Redis's speed isn't a happy accident. It's the result of several deliberate architectural choices. Being in memory eliminates disk latency. The single-threaded model eliminates lock contention. I/O multiplexing allows for massive concurrency. Optimized C data structures minimize memory footprint and CPU cycles. and background persistence ensures your data stays safe without slowing down the hop path. Whether you are building a real-time leaderboard, a session cache, or a message broker, understanding these internals helps you use Redis to its full potential. Next time you see a 0.1 millisecond response time, you'll know exactly what's happening under the hood. Thanks for watching.